You're a product manager named Alex. Legal sends a dense 10,000 token contract and asks a simple question: what are the termination clauses? Alex drops it into a model with an 8,000 token limit, gets a confident answer, and ships it to the team. Later, legal replies. 2 key clauses near the end were missed. Alex didn't change the question. The model just didn't see those pages. That moment feels mysterious until you realize there's a hard edge to what these models can hold in mind at once. The context window is the working memory. It's not vibe. It's a fixed boundary. Here's how I like to think about it. Imagine a stage covered in text. The model shines a spotlight that's only so wide. Everything inside the light can be compared, connected, and reasoned about. Anything in the dark doesn't exist to the model, and unlike a real spotlight, there isn't a gentle fade. It's a sharp cut. If your paragraph sits 1 token past the edge, it may as well be on another planet. Quick check. A context window is measured in tokens, not characters, and not words. A token is a small chunk of text, often a few characters or part of a word. So at this point, we have a simple picture. The model can only see a certain number of tokens at once. That's the first half of the puzzle, what fits inside the light. Before we go further, let's ground the mechanism, because once you've seen it, the trade-offs make sense. Don't worry if this feels abstract. The example with Alex will make it concrete. The first thing the model does is tokenize the input: system prompt, your instructions, previous chat turns, and the document itself, until it hits the maximum. If the total exceeds the limit, the oldest tokens typically get dropped, or the text is truncated to fit. To put it plainly, exceed the window, and earlier parts just vanish from the model's view. From there, each token becomes a vector of numbers called an embedding. Position information gets woven in, so the model knows that token A came before token B, and roughly how far apart they are. The engineering behind this is genuinely clever. Thousands of tokens get mapped into a geometric space where meaning is distances and angles. Here's where it gets interesting. Inside the spotlight, every token compares itself to every other token. That comparison is called self-attention. Each token asks, which other tokens matter to me right now? Those comparisons are computed with 3 learned vectors called queries, keys, and values. A token's query checks for matches against every other token's keys. The best matches get higher weights, which then mix the values into a new blended representation. That's how context becomes meaning. Let's pause there for a second. 1 token looking at all tokens means you're building a big square of comparisons. Double the tokens and the size of that square quadruples. That's the fundamental cost driver. To put it simply, longer windows grow compute and memory roughly with the square of the length, not the length itself. That's why pushing from 32K to 128K tokens isn't 4 times harder. It's about 16 times more attention work per layer before you count the rest. If you're keeping score, we've got embeddings feeding into attention feeding into layers, and layers stacked on top of each other. Each stack refines the context understanding a bit more. Then the model predicts the next token, one by one, auto-regressively. Fair warning, this next part is dense, but it's the heart of the trade-off. Every layer repeats full window attention, not just once, many times across multiple heads. Multiply a big square by many layers, and you start to feel why long context is heavy. Let's anchor that with our scenario. Alex's 10,000 token contract doesn't fit into an 8,000 token window, so the model chops the early history, or the tail of the doc. Often, the tail goes. The termination clauses near the end simply aren't in the light anymore. This is what's happening when your chat forgets things. It's not memory loss in a human sense. It's a hard capacity cut. You've probably seen this without realizing it. Long support threads where the bot stops recalling what you said an hour ago. The context window was full, and the first message is aged out. Here's the twist most people don't expect. Even when text is inside the window, the model doesn't pay equal attention to every spot. There's a well-documented lost in the middle effect, where items at the very beginning and end tend to get more weight than details buried in the middle. To make that practical, if something really matters, place it near the start or the end of your prompt, not the exact center of a long block. At this point, you might wonder, why not just make the spotlight enormous? Some models do. You'll see claims of 128K tokens, 1 million, even 2 million. And here's the part that still amazes me. At those scales, the model is considering relationships across entire books, source trees, and hours of conversation. That's wild. The catch is cost. The attention matrix grows with the square of the window. 1 million tokens means a trillion potential pairwise interactions per head per layer. Vendors use optimizations, sparsity, and clever chunking, but you're still paying for a huge field of light. Quick reset. Context size buys reach across long-distance dependencies, but it taxes memory and latency in a big way. This connects directly to decisions you make in products. Do you stuff a long document into the prompt and hope the model finds the key bits? Or do you retrieve the most relevant chunks and keep the window small? Here's the intuition to hold on to. Long context is like widening the spotlight. Retrieval is like moving the spotlight intelligently to the parts you care about. Back to Alex for a moment. Using an 8K model on a 9,500 token contract forced truncation and risked hallucinating missing end clauses. A model with a 2 million token window can fit it all, but the attention grid at that scale is mind-bendingly large. In practice, many teams split the difference. Use retrieval to pull 2 or 5 relevant passages into a modest window, then reason deeply within that. If you're keeping track, we've covered the what and the why expensive. Let's walk through the parts end to end with concrete numbers, so it sticks. Imagine the 9,500 token contract. Tokenization counts every subword piece. If you feed it to an 8,000 token model, the last 1,500 tokens won't be seen unless you drop earlier content. Either way, something falls off the edge. That's why the model never mentions the last termination clause. It literally wasn't in the input. Now suppose you pick a long context model. The attention matrix for 9,500 tokens is roughly 90 million token-to-token scores per head per layer. A 2 million token window implies around 4 trillion scores per head per layer before optimizations. That's the scale we're talking about. To put it simply, bigger windows mean dramatically more compare and mix work, repeated many times. More GPU memory, more time, more dollars. Here's what most people get wrong. They assume longer windows guarantee perfect recall. In reality, attention is probabilistic and learned. The model can overlook details that sit in the middle. It can also get distracted by noise. I'll be honest, this took me a while to really get. Signal to noise inside the window matters as much as raw size. A crisp, well-placed prompt often beats a bloated one. This is what's happening every time you use a code assistant on a large repo. The assistant doesn't ingest the entire code base into context. It retrieves the most relevant files, often via embedding search, and then reasons within a small window. Same for enterprise chat. A vector database fetches passages, not entire document libraries. In production systems, this is where guardrails live too. System prompts, tool instructions, and policy text all consume part of the window. Output tokens also count against the budget. Your memory isn't just user text. It's everything the model sees and everything it's about to say. Right now, the mental model is clean. A fixed spotlight, quadratic attention inside it, and practical tricks to move the light to the right place. That's the core. Let's bring in a few pitfalls and how to handle them. First, the fixed size forces a sliding window in long chats. As new tokens arrive, older ones fall off to stay within the limit. That's why a model remembers the beginning of a call and the last few lines, but loses the middle as the conversation grows. Second, the lost in the middle effect. If a crucial fact is at token 5,000 inside a 10,000 token prompt, there's a decent chance it gets underweighted. One simple countermeasure is placement. Put key facts at the top or bottom of your prompt wrapper, near your instruction. Even a one-line reminder near the end can help. Third, truncation choices matter. Some frameworks trim earlier user turns, others trim the latest document tail. If your system always keeps the most recent chat but chops the end of a file, summaries can drift. Know your defaults, because they silently shape model behavior. To keep us oriented, we're talking about the ways context can fail even before you consider model quality. Placement, size, and noise decide what the model can use. When you think about what's actually happening here, it's remarkable. In under a second or two, a model can thread connections across thousands of tokens, across dozens of layers, and produce fluent language that often lands. The fact that any of this works in real time still feels like science fiction made practical. Okay, deep breath. Let's turn this into working heuristics, the kind you can apply tomorrow. If a document is more than, say, 20% of your context window, consider retrieval instead of stuffing. Break it into chunks, index with embeddings, and fetch the top few passages relevant to your query. Place critical details near the start or end of your prompt wrapper, not buried dead center. This single change improves recall more than people expect because it sidesteps that middle dip. Test the limits explicitly. Ask the model to repeat or use a detail placed halfway through the prompt. If it misses it, rework your placement or switch strategies. A simple, repeat the number 732 from the section above reveals if you're beyond the model's comfort zone. Keep prompts lean. Extra prose dilutes attention. If you can say it in 10 tokens, don't spend 50. The model is balancing a budget, and clutter competes with your priorities. In production, budget for output tokens too. If you expect a long answer, reserve space. A 32K input doesn't help if the model has no room left to respond. Plan for both sides of the window. If you're a PM like Alex, here's the practical upshot. For long docs, retrieval plus a moderate window is usually the sweet spot for cost, latency, and reliability. Save ultra-long context for cases where the dependencies span the whole document and can't be pre-selected, like complex legal analysis where clauses reference definitions sprinkled throughout. So far so good, we've aligned the tool to the job. Bigger isn't inherently better, smarter use of the budget matters. Under the hood, this is also why long context-tuned models exist. They use special positional encodings and training schemes to maintain accuracy as the window stretches. Without that tuning, a model might accept long inputs but melt in quality near the edges. If you're keeping score, we've covered definition, mechanism, cost, failure modes, and practice. 2 quick misconceptions to wrap. 1. Context window isn't just your chat history length. It includes system instructions, retrieved snippets, and the model's own output. The total has to fit inside the window. If you forget the output side, you'll get clipped endings. 2. Longer windows don't mean the model stores everything perfectly. They expand what can be considered in one shot, but attention still prioritizes. Placement and pruning still matter. Back to Alex for one last look. The team tried the 8K model and missed the ending. Next, they tried a giant window, and it worked but felt slow and pricey. The final solution used retrieval. Grab the sections with termination, cause, and notice headings, plus the definitions section. Then ask a moderately sized model to answer with citations. Legal felt confident. Latency dropped. Cost dropped, and accuracy improved because the spotlight landed where it mattered. If you're listening along, the story ends where it began, with a boundary you can steer. The context window is the working memory of the model. You can widen it, you can move it, and you can curate what goes inside. That's most of the game. To put it simply, decide whether you need breadth or focus. Use long context when the relationships truly span the entire text. Use retrieval when you can target. Keep critical details at the edges. Budget for output, and test the middle. And one more quiet appreciation before we close. The fact that these systems can weigh relationships across thousands of tokens, in parallel, across many layers, and do it interactively for everyday work. That's a serious achievement in applied math and engineering. Where we are now is powerful, but you don't need to chase the biggest number. You need to master the spotlight. If this helped clarify how context windows work, a like and subscribe helps us make more of these.